This is Dr. Holt, and this problem here, I have a thin rod of length L. It's going to be pivoted at one end, and it's going to be pivoted right here at this location here. Okay, it's going to be free to move at this point. Now, the moment inertia of the rod is given as 1/3 ml squared, meaning the rod are being rotated about this end here. And then we're also given the moment inertia of the sphere as 2/5 mr squared, and it's about its own center. What we want to do here, we want to find the angular acceleration of the rod immediately after it's being released. What's taking place on this one is you're going to have a torque that's going to be taking place because you have this mass times gravity pulling down. You have this rod, the mass of the rod, times gravity pulling down also. Both of these are going to create a torque around this axis. Now we know, we'll do some red, that torque is going to equal to the moment inertia times the angular acceleration. And we're going to be working primarily with this to get the angular acceleration as it quoted below. Alright, so first thing we want to do on this one is we want to find out what the moment inertia is of the system about this point. So we will say the moment inertia, and let's indicate this as point A. The moment inertia around A. Now again, this equation here is given as a rod about its own end. You could use the equation, find the moment inertia of the rod about its own center of gravity, and then use parallel axis theorem to get back to that A, but you're going to get the same thing. So we will put 1/3 times m times L squared. Now we'll go to the sphere. The sphere is given as 2/5, put the plus, 2/5 m, and then we want to do the radius. Now the radius is going to be 1/6 L, and we need to square that. Alright, now this is not the entire moment inertia. This mass is out here from this distance here. You need to use a parallel axis theorem on this and include plus mr squared, or m length squared, or whatever you want to call it. We have to include that because this value here, the 2/5 mr squared, is only moment inertia at this point. You've got to use parallel axis theorem in relationship to the point of rotation. So we're going to do that now. So that's going to give me, change it. That's going to give me plus the mass of this object here times the distance, which is going to be 7/6 times L times squared. And the reason I got 7/6 from here to here would be 1L, and then I add another 1/6. So 6/6L plus 1/6 gives me this value right here. Scroll down a little bit. Okay, we'll go ahead and calculate that. When I run that value, I think I get, let's say, 1/3 ml squared plus 1/90 ml squared plus 49/36 ml squared. So we add all those up. The moment inertia around point A would equal to 307 divided by 180 ml squared. Okay, so that's my moment inertia. Now let's do the torque, because we're trying to do this. We've got this value here now. Now we need to find out what this value is, but to do that we need to find out what torque. Alright, so I'm going to let anything that goes this way be negative using standard convention. When I do that, let's take this. The summation of torques about A is going to equal to, okay, when I located this originally, I should have put it right in the middle of the this mass here. This is actually the center mass of